Processing crude oil at scale requires a massive, continuous chemical operation. Within these operations, a specific shift in fuel sourcing is underway. India's public sector oil refiners are officially integrating 30,000 metric tons of green hydrogen annually. The capacity is split across 4 state-backed facilities, 10,000 tons each for Indian Oil's Panipat and Numaligarh, and 5,000 tons each for Bharat Petroleum Bina and Hindustan Petroleum Vizag. Petroleum refineries currently represent the largest domestic consumers of hydrogen in India. Replacing the traditional carbon-heavy gray hydrogen with a clean alternative requires overcoming high capital costs and the operational risks inherent in a new technology. To address these specific bottlenecks, the Ministry of New and Renewable Energy established the Site Mode 2B framework. Achieving commercial parity for green hydrogen in heavy industry depends on a specific financial architecture that prioritizes demand aggregation. To understand the shift, we have to look at the ground-level engineering of a refinery. Hydrogen is used for hydrocracking and desulfurization, the critical chemical processes stripping sulfur impurities from crude. Traditionally, this hydrogen is produced on-site through steam methane reforming, or SMR, using imported natural gas. This gray hydrogen flows directly into the refining units. However, the SMR reaction vents significant CO2 as a byproduct. This model leaves the refiner dependent on global gas prices, creating a vulnerability in energy security. While gray hydrogen meets chemical needs, it creates long-term exposure to both emissions mandates and volatile foreign feedstocks. By contrast, integrating green hydrogen through advanced water electrolysis completely removes the heavy CO2 output from the chemical equation. This chart shows the primary barrier, a massive cost delta between green and gray hydrogen due to the high capital expense of electrolyzers. Replacing the carbon-intensive SMR units requires a pathway to bring these costs down. Site Mode 2B changes the market dynamic by using demand aggregation rather than individual pilot projects. The framework bundles the requirements of all 4 refiners into a single 30,000-ton procurement block. This immense volume allows developers to leverage economies of scale, lowering the per-unit production cost. By consolidating the market, the policy creates a bankable structure for large-scale investment. The next challenge is funding the massive upfront capital required for these electrolyzers. Under the build-own-operate model, refiners don't build production units, private developers do. This moves capital and operational risks off the refiner. In exchange, developers get a long-term offtake agreement, guaranteeing the refinery buys the fuel at a set price. Guaranteed contracts from a state-backed refinery allow developers to secure financing at a lower cost of capital. This critical financial de-risking officially allows the massive physical construction of green, renewable energy infrastructure to finally begin. Ultimately, the BOO model ensures refiners focus heavily on consumption, while private developers are inherently incentivized to optimize production efficiency. Integrating 30,000 tons of green hydrogen under this framework impacts the national economy across 3 specific vectors. First, industrial decarbonization. Using green hydrogen directly offsets the CO2 emissions traditionally linked to crude refining. Second, scalability. The long-term offtake mechanism reduces capital costs toward commercial parity. Third, energy sovereignty. Replacing imported gas with domestic renewables insulates the economy from global market shifts. These macro-level shifts are designed to integrate into the daily operational reality of India's logistics and energy infrastructure. Site Mode 2D demonstrates that bridging the green premium in heavy industry requires financial innovation as much as chemical engineering.